if there are no questions, we are going on with the material. Okay, so we are still talking about the method of implicit differentiation. Last time I already roughly explained what this method is about. This is a very important method, and actually you have used it already in high school, but maybe you are not aware of this. So once more, until now, most of the time when we saw a function, the function was given explicitly, which means that you had an expression like this here, y is equal to f of x. Okay, so this means the function is given explicitly. Now we are talking about functions which are given implicitly. This means that actually you just have some function in two variables depending on x and y is equal to 0, and very often you are not able to solve for y, or you are able to solve for y, but the resulting expression is quite complicated compared to the implicit definition. So this is what I explained. For instance, some examples for functions which are given implicitly. We saw last time already. So for instance, this function here. Okay, we know that this function here describes the circle, or this equation here describes the circle. And if you can solve for y easily. You have two solutions: one describing the upper semicircle, one the lower semicircle. And we saw also another example, x to the cube plus y to the cube is equal to 6xy, the so-called volume of the car. Here in this case, it's already more complicated to solve for y. Okay, and our aim is to find. So we assume that y we can solve. If we can solve for x, y will be a function of x. Okay, and under some conditions, this function might be differentiable. We want to find the derivative. Okay. Now, as I have explained last time, this method of implicit differentiation, okay, does not solve first for x and then compute the derivative, but you immediately compute the derivative from this equation here. Okay. So, for instance, for this example here, okay, you see you don't have to solve for y. You can just assume that y is a function of x, and then you use the chain rule in order to handle this term here. So you see that. Okay, now it works. I will show you some examples in Maple in a minute. Okay, so if we look at this example here, we see actually we do not have to solve first for y. We can immediately find the derivative by just taking the derivative on both sides. So we have 2x plus, and here we have to keep in mind that we have to use the chain rule. So we assume that y is a function of x. So we have 2y. Derivative of y is equal to 0. And now we just solve for the derivative of y. So what we get then is minus x over y. Okay. So for instance, if you are interested in a point, what is a point which lies on this curve? So for instance, 3, 4. Okay. If you are interested, okay, what is the tangent at this point? You can directly work with this expression for the derivative. So you see that the derivative at the point 3 is equal to minus 3 over 4. Okay. So you can already from here you can find the equation of the tangent, which is minus 3 over 4 x minus 3 plus 4. Okay. And of course you can simplify this. So you see here, this approach is much more convenient, okay, than first solving for y, which gives you not a complicated expression in this case, but a more complicated expression than this would be here. So if we solve first for y, we would get y is equal to plus minus the square root of 25 minus x squared. Okay, and also from here we could compute the derivative, but we would get two derivatives, one for the function describing the upper semicircle, one for the lower semicircle. And if you are again interested in the tangent at this point here, what you're going to do is you choose the one which describes the upper semicircle, because this point lies on the upper semicircle, and compute the the tangent. So you see, for this example, it's not a big difference, okay? But you see already some differences which are essential. Namely, if you solve first and then compute the derivative, you would get two derivatives, but those two are here merged into one expression. Okay, this is already an advantage. Okay, so actually, of course, what you get is just the same expression. So but you have minus plus and then x over the square root of 25 minus x squared. But here you have only one expression. You have merged them into one expression, so which is more convenient. And also, computing the derivative is here slightly more easier than it would be here. Okay. So once more, this method, the method of implicit differentiation is okay. You have given a function implicitly. Okay. You do not first try to solve for y. You just start from the defining equation, take derivatives on both sides. Normally, this involves using the chain rule at some point, and then you solve for the derivative, because normally what you get is a equation, first order equation. You solve for the derivative, and that's the way we compute the derivative. Okay. Now, actually, this method here, of course, needs some assumptions. Namely, whenever you can use it whenever you have such a function here. Okay, such an expression, such an equation. But what you need to know is that actually you can really solve for y. You have a function y of x, which is the solution of f of x, y of x is equal to 0. This is the first thing you have to know. And the second thing you have to know is that this function y of x is differentiable. Okay. Normally, the reason why you use this method is because it's complicated to solve, either complicated to solve for y, or it's not possible to do it in the case that you can write down the function. Okay. Still, you have to know, just by looking at this equation, you have to know, okay, under which assumptions does there exist a function? Under which assumptions can you solve for y? And this is the first thing. And the second thing is, under which assumptions is the resulting function differentiable? Okay. We are not going to discuss this here. So we always assume, if we use this method, that there is a function which is solving. If you plug in the function here for y, it solves this equation here. And we always assume that the function is differentiable. The real justification for this method is, as I have explained last time, is a deep, complicated theorem in real analysis, and you will learn it in, I guess, in other classes. Okay, so for this example, this is not so. Actually, we do not really have to rely on the method of implicit differentiation. So let's look at the second one, where it would be more complicated to solve for y. Okay, so I showed you already last time, so we can take the derivative on both sides with respect to x. So here we get 3x squared plus, and here we have to use the chain rule, so 3y squared times the derivative of y is equal to, here we have to use the product rule, so we have 6y plus, and then 6x derivative of y. Now you solve this for y, for the derivative. Okay, and what you get is 2y minus x squared over y squared minus 2x. So you see, this is the derivative of the function implicitly given by this equation here. Now, if we again choose some points, or let's say which point does lie on this curve, you easily check 3, 3. Okay, so you see, just by using this expression here, you have the derivative at 3 is equal to, so you have 6 minus 9 is minus 3. And here the same, plus 3, so you have minus 1. Okay, this is 9 minus 6. Okay, it's correct. So the tangent will be minus x minus 3 plus 3. Okay, so you have minus x plus 3 plus 6. Okay, so for instance, you can find easily, like this here, the tangent at some point. Now, I last time showed you already, if you would plot this function given implicitly by this equation, I will show you this in a minute, how to do this using Maple, then the graph looks like this here. Okay, so the point we have discussed here is exactly this point here. Okay, and you see already a little bit from the graph, okay, that the tangent has slope here -1, and it's kind of and it's also shifted. Okay. Now, so any questions how to use this method? For instance, you can also use this now in order to figure out, okay, questions like for which points at this curve is the tangent horizontal. I think this is one of the questions which is discussed in the textbook. Oh yeah, where is the tangent horizontal? So if you want to know where is the tangent, at all the points where the tangent is horizontal, maybe I copy this expression here once more. And our original equation was x to the cube plus y to the cube is equal to 6xy. Okay, so then you have to equate the first derivative equal to 0. So you see that from this you get that 2y must be equal to x squared. Okay, so now what you do is, okay, so y must be equal to x squared half, and you plug this into the original equation. So you have x to the cube plus x to the 6 over 8 is equal to 3x to the cube. Okay, so from this you get that 5x to the cube. No. 8, 20, 24. Okay, 23. X to the 24, 18. Minus x to the 6 is equal to 0. Okay, so now you can take out x to the cube, and you have 18 minus x to the cube is equal to 0. Okay, so you see from this equation that x is equal to 0 is one point here, which is correct, because in this case you have also y is equal to 0, so you get actually this point here. So you see that the tangent here is horizontal, and you see that here you have another point. So x must be equal to the square root of 18. So this would correspond then to this point here. So from the graph you already see that you must have 2 points where the tangent is horizontal. Okay, you see that without really, but if you have given such an equation, most of the time you do not know how the function looks like. But this doesn't matter. Without really knowing how the function looks like, you can still figure out here questions like at certain point, what is the tangent and where is the tangent horizontal and so on. So this is the convenient thing about the method of implicit differentiation. Let's maybe look at another example. Now, here for such an expression, it would be complicated to solve for y here. Actually, it's not really possible. Okay, but we can still assume that okay, or at least we assume that there is a function y of x solving this equation here, and that the function y of x is differentiable. Okay, if we have this assumption, we can easily find again the derivative. Namely, we just at both sides we take the derivative with respect to x. So we have here 2x minus. Now here we have to use the chain rule, so we have the cosine of xy times the derivative of the inner function, which is y plus x derivative of y plus the derivative of this part here, which is 3y squared derivative of y is equal to 0. And again, this gives us a first order equation of first order, a linear equation for the derivative of y here, and we just solve it. Then we get that the derivative of y is equal to, so we have cosine of xy times y minus 2x over, and here we have 3y squared minus x times the cosine of xy. Okay, so, actually you should realize here from this function, actually we do not have a picture, okay, unless we rely on a program like Maple to plot a picture of this curve here. It's the first thing. And the second thing is, actually we do not even know whether this equation here can be solved for y and whether the resulting function is differentiable. But if there is a solution and the function is differentiable, okay, this must be the derivative. Now, again, if we look at the point, this point should lie on this function here, yeah, on this curve here. So you see that the derivative at 1 is equal to, so you plug this in here, so this is 0, this is minus 2 here, over, this is 0, this is 1 here, so this is minus 1, so it's equal to 2. So you see that the tangent at this point here would be 2 times x minus 1, so 2 times x minus 2 here. So without knowing how this function here looks like, you can still compute things like the tangent at certain points and so on and so forth. But of course, it would be nice to have a picture, okay, to check this, whether this is whether this function first is really solvable locally around this point here, and whether this corresponds, whether this is really the right answer. So in order to do this, a good tool is Maple, because Maple is able to plot functions which are given by such equations. Okay, so maybe let's look first at this example here. So once more, the equation here of this curve was x to the cube plus y to the cube is equal to 6xy. Now, I first show you that actually this can be solved. This can be solved for y. Okay, you haven't learned in high school. You have learned in high school how to solve quadratic equations, but you haven't learned how to solve cubic equations. There is a formula, a similar method for solving such equations, and it's implemented in Maple. So this is our equation which we want to solve. Maple is able to solve equations. The comment for this is solve. Okay, and then you have to tell Maple, okay, for which variable, y here in this case. So solve this equation for y. Okay, so you see that it takes a little bit of time, but Maple has no problems in order to find the solutions. The solutions are not so easy in this case. That's the reason why you haven't learned the formula for solving cubic equations, because it's more complicated than quadratic equations, as you see from this expression. But it's not too nasty. So maybe you see there are 3 solutions. Actually, you observe here something which is quite curious. You see this one is the first solution. The second one is this horrible thing here, okay? And you see that there is an I inside the solution, okay? So actually, this I is the imaginary unit from the complex numbers. Okay, you have learned this in high school, right? Complex numbers you have learned in high school. So this I is a number where the square root is equal to minus 1. So actually, the second and the third solution looks like it's a complex function, okay? But this is not true, okay? If you plot this, so actually, if you try to simplify this, it's possible to rewrite this such that it becomes a real function. This is a well-known case for cubic equations. So maybe it's interesting to plot the functions which are involved here. Let's plot first the original the complete function. So this function given implicitly by this equation. So just to show you how to do this by using Maple. So if you want to plot something like this here, Maple has a package so Maple has the usual plot comment, which I showed you already previously, but Maple has also a package where you have many more comments which allow you to plot all kinds of more complicated functions. Such packages are normally used by with, so you load in a couple of comments. Okay, it's called plots. Okay, so this package is called plots, and you see now you have a couple of more comments. Okay, so you can do all kinds of things, all kinds of fancy things using Maple. You see there is one comment which is called implicit plot. Okay, over there, here, and this comment is used for plotting functions which are given by implicitly, which are given by equations. So we use this implicit plot. Now we just plug in the expression. Okay, and we have to give a plotting window. So we plot it over, let's say, x from -3 to 3, and y, or let's plot it from -3 to 5, and y from -3 to 5. Okay, so here you see the graph, as I have claimed. Now, you see something, it doesn't look very pretty, okay? The main problem is, so plotting implicit functions for Maple is not that easy, okay? Because the only thing what Maple can do is try some points, okay? Compute a couple of points, plot them, and then connect them. But normally, if you have something like this here, if the curve is crossing itself and something like this, Maple will have big problems, okay, using the method. But if you find this too ugly, then you can tell Maple use more points. So you can actually set the number of points Maple is using for doing this computation. So let's maybe use 3,000. Okay, now it looks slightly more pretty, but you see still the point 0 is a problem, because here the essential reason is because the curve is crossing itself at this point here. Okay, this is this function here. As I have explained to you last time, and as is also explained in our textbook, if you would plot the three functions which you get a solution, then one part is just this here and this here and here some part. The second function would give you the other part of this loop here, and the third function gives you here some part. Okay. Also, this is explained in our textbook. The three functions which you saw from the explicit solution can be plotted like this. Now, maybe let's look at this function here, because we have done here the computations without actually knowing how the curve looks like. So maybe it's interesting to see how the curve looks like. Okay, so here we have x squared minus sine x times y plus y to the cube is equal to 1. Now, the plotting window, of course, is kind of random. You have to choose you have to try a little bit around to find the right one. Now, and also let's do more points. So maybe 3,000. Okay, so do you see this is this curve here, and we just computed the tangent at the point 1, 0. Okay, which happens to be this point here, which crosses the x-axis, and you see that we saw that this is the equation. Somehow from this here, if you draw here the equation, you would see, okay, it's quite correct. For instance, you see that if you plot it over a larger window, you see that the tangent, okay, is somehow intersecting with the y-axis at -2. So it seems to be correct. In particular, it seems to be correct. What is certainly correct is that the slope is positive. Okay, and it looks if you plot here the tangent, the slope looks more like 45 degrees, so 2 is also kind of reasonable. Okay, so of course you can do such exercises, okay, without ever understanding, okay, how the function looks like. So you can still compute the derivative and so on. But using Maple is a convenient tool to check whether your answers make sense and to get the feeling how the function looks like. Another function which is also quite interesting. is this one. X squared plus y squared is equal to 2x squared plus 2y squared minus x squared. Okay, so also here for this function, if you're interested, for instance, the points, which one? 0, 1/2 seems like this is 1/4. Yeah, 0, 1/2 is a point here on this curve here. Okay, so you see that you can easily, by using implicit differentiation, you could easily find the derivative at 0 and then find the tangent and so on. I'm not going to do this. I just show you how this curve looks like. We will encounter this curve at the end of this semester, next semester quite frequently. So if you haven't downloaded Maple yet, do it. Okay, let's maybe choose -1. And more points. Oh, even more points. Not enough. Not enough. Maybe more. Okay, now it already looks quite okay. So this is another important curve we will discuss at the end of this semester. This curve has also a name. This curve is called cardoid. This is, if you have, I don't think you learn Latin here in Taiwan, but if you have learned Latin, then you can guess from this name it means heart. Okay, and you see the curve looks a little bit like a heart. So this is the heart curve. Okay, so but you see also here, without knowing actually how the function looks like, you can still compute derivatives at certain points. You can compute tangents and so on by using the method of implicit differentiation. You will find more such curves in our textbook. If you download Maple, you can also try a little bit around to try to find some pretty looking curves. I should maybe stress once more, okay, that of course if you have given a curve, a function like this here, okay, you cannot be sure, okay, that there is really a function y of x satisfying this equation, okay, because for instance this one, no chance that you can solve it for x, okay, and you cannot be sure either that this function is differentiable. So this method, the method of implicit differentiation, once more certainly needs conditions, okay. So you have to you need condition which ensure, okay, that just by looking at such an equation, okay, you can solve it for y and the resulting function is differentiable. And such conditions will be provided by a theorem which is called the implicit functions theorem, and this you will learn in another class. So most of the time we are just using the method of implicit differentiation without really justifying that we are allowed to do it, okay. But the conditions are quite weak, so in most of the cases you can use this method. Now, another application of the method of implicit differentiation is we already discussed, or something which you already know from high school. We already discussed that the derivative of this function is n times x to the n minus 1. But actually, if you recall our proof was just for n being integer. Okay. For in all other situations, I haven't provided the proof yet for this rule here. Okay. To remind you, the case where n is larger than 0 is quite easy. Here you use the binomial theorem, and for n is smaller than 0, okay, you write this here as 1 over x to the minus n, and you use the quotient rule. Okay. Now, if you, for instance, want to handle the case where n is a fraction, okay, so in this case, we look at the function y is equal to x to the p over q. Okay. Now you see that you can write this as y over q is equal to x over p. Okay, and here you can use the method of implicit differentiation. Okay, because both q and p will be integers, and we have proved already, we have considered already this case. Okay, so you see that if we take derivatives on both sides, you have q y to the q minus 1 is equal to p times x to the p minus 1. Okay, and sorry, there is a derivative missing, p x to the p minus 1. So you see that the derivative of y is equal to p over q x to the p over q minus 1. As I have claimed already, because I said that this rule actually holds for all real numbers here, okay? But you see, now this proves the case where n is a rational number. So we have proved now that the derivative of a power function is equal to n, or derivative of a function x to the n is equal to n to the x to the n minus 1 for all rational functions. Okay. Also, so here you need the method of implicit differentiation. So this is another application of this method here. Now, one final thing which is related to this topic and which is also discussed in our textbook are so-called orthogonal trajectories. I'm not sure whether my spelling is correct. Trajectories. No, there is an E, sorry. Okay, so what is this supposed to be? This is something which is important in physics. We say normally the two curves are orthogonal if in every point of intersection of the two curves, the two tangents are orthogonal or perpendicular. So two curves are called orthogonal. If in every point of intersection the tangents are orthogonal. And now two families of curves are called orthogonal trajectories. Okay, so two families of curves are called orthogonal trajectories if every curve of the first family is orthogonal to every curve of the second family. Is orthogonal to every curve of the second family. Okay, this is actually something which you have seen in physics quite frequently. So, for instance, the streamlines. or the lines of heat, okay, and the so-called isotherms are orthogonal trajectories, or if you have a electrostatic field, then normally the line of forces are orthogonal to the lines of constant potential and so on. So normally you have many examples for such orthogonal trajectories coming from physics. Let's maybe look at the concrete example just to make this clear what I mean by this. Okay, so for instance, if you look at the following two families of curves, x times y is equal to c, where c is not equal to 0. So this is the first one. And the second one is x squared minus y squared is equal to k. K is not equal to 0. So actually what you have here is hyperbolas. So for instance, suppose the family, this first family here is described by this parameter c, and if c changes, you get different curves. So for the first one, we know that, okay, for instance, the case where c is equal to 1, we get this one here. And then similar curves, if you change the parameter c here. If c is negative, you also get this one. And so on. You have then similar curves for changing parameters of c. And if you plot this here, for instance, for k is equal to 1, we know that, okay, what we have is it's not correct, not really correct how I draw this, but okay. Okay, now it doesn't look like this from my picture, but actually, whenever you see a point of intersection here, okay, you have here a right angle between the tangents, okay, here it's not really correct, so I should draw it a little bit different. And this actually holds for all This holds for any orange curve you choose and any yellow curve you choose. In all points of intersection, the tangents will be orthogonal. Now, this is actually easy to prove from the equations. You do not have to solve for y or something. You can use just directly the method of implicit differentiation. If you do this for the first one, in order to compute the derivative, you see what you get is y plus x times the derivative of y is equal to 0. So the derivative of y is equal to minus y over x. And if you do this then for the second one, you see 2x minus 2y times the derivative of y is equal to 0. So here now the derivative of y is equal to x over y. Okay, and from this form of the derivative, okay, you see already that because this is the this is 1 over this one and negative, so you see already that in all points of intersections, the tangents must be orthogonal. Okay, so you see that checking whether two families of curves are orthogonal trajectories or not, you can also just directly start from the defining equation. You use the method of implicit differentiation, and you can find like this the derivatives, and this already proves that those two families are indeed families of orthogonal trajectories. Now, this is another application of the method of implicit differentiation, and maybe the most important for us, and the one which you have already seen in high school, I guess, is that you can use the method of implicit differentiation to compute derivatives of inverse functions. Maybe just to remind you, we have found already the derivative of polynomials, rational functions, exponential functions, and trigonometric functions, and also hyperbolic functions, but not yet the derivatives of the inverse functions of those functions. we have waited till now because we need for this the method of implicit differentiation. So okay, so we have given the inverse of some function. Now, by definition, this means that f of y is equal to x. Okay, and you see, you can interpret now the function, the inverse function, okay, given by this implicit equation here, by this equation here. Now, actually, we already know here, okay, because normally we know that the function has an inverse function, so we know that the equation can be solved for y. This is not a problem here, but we still have, in order that we can apply the method of implicit differentiation, we still have to figure out, okay, does the derivative, okay, of the solution exist? Okay, is the solution of this equation here differentiable? Now, there is a theorem which I state without proof. Okay, so if f is 1 to 1 and differentiable, and has no horizontal tangents, then the inverse function is differentiable. This is something you actually expect because the graph of the inverse function, we obtained it by taking the graph of the function f and reflecting it about the line y is equal to x. Now, by this simple reflection process, okay, you would expect that if the original function is differentiable, the inverse function will preserve the property of being differentiable. The only problems you have is that if the original function has horizontal tangents, okay, because those horizontal tangents by this reflection principle are mapped into vertical tangents, okay, and vertical tangents are points where you have a vertical tangents are points where the function is not differentiable. So I'm not going to prove this here, but if you know this, okay, then you can just look, by looking at this equation, okay, you normally know that the function is 1 to 1 because you want to invert it, okay, and by looking at the function f and figuring out that the function f doesn't have any horizontal tangents, okay, you can use the you can already deduce that the solution of this equation here will be differentiable. So in this case, the assumptions for applying the method of implicit differentiation, actually I told you before, we do not care in most of the cases about the assumptions. We just use the method of implicit differentiation. This is the only case where we care about the assumptions. Okay, so we need this theorem, and we need that the function is 1 to 1. Then we can use here the method of implicit differentiation. So you see that by taking derivatives on both sides, you have the derivative of f at y times, so this is the composite function times the inner derivative is equal to 1. So you see that the derivative of the inverse function is given by 1 over f, the derivative of f, and plugged in the inverse function. Okay, so this is the formula how you compute the derivative of inverse function. So actually what you do is you just write the inverse function, okay, in terms of the original function, and then you use the method of implicit differentiation in order to find the derivative. So for instance, if we look at trigonometric functions, I guess you have done this in high school. So for instance, if you look at trigonometric functions, so for instance this here, then okay, so you can rewrite this as the sine of y is equal to x, and actually you also have that y must be between minus pi half and pi half. Okay, and now you apply here the method of implicit differentiation. So you have the cosine. The sine of y becomes the cosine of y times the derivative of y with respect to x is equal to 1. So actually you just do the same as here. This means that dy over dx is equal to 1 over the cosine of y. And now for this, okay, so you know that the cosine of y is equal to plus minus the square root of 1 minus the sine square of y. Okay. You also see that because we have for y we have this range here, but in this range the cosine of y is positive, so it's certainly not the minus solution. So you can discard the minus solution. Okay, so this is not the right solution, and you just plug this in, and you get, and then you plug in for y the inverse sine of x, and you get that the derivative of the, maybe let's write it like this, of the inverse sine function of x is equal to the formula you might have learned already in high school. Okay, so I guess you have seen this method in high school. Okay, the only thing which is new for you, which you should realize here is, okay, that in order to do this, maybe you have used the same method in high school. Okay, but in high school you haven't thought about, okay, are you allowed to do this? Okay, you have just done it. But actually you need assumptions here. Okay, now the reason why we can apply the method of implicit differentiation here to this equation is, okay, because first of all we know we can solve for y, certainly, because we know the solution is the inverse. Okay, we can solve for y, and we know the resulting function is differentiable. Okay, because the sine is differentiable and doesn't have any horizontal tangents. You might object here, but here the sine is just in this range. Okay, here we do not have horizontal tangents. Okay, so this is the derivative, and similar, you can find that the derivative of the inverse tangent function is, this is actually important, is 1 over 1 plus x squared. You just use the same approach as the approach which I used here in order to find the derivative of the inverse tangent function. And similar, you do it for the inverse cosine, the inverse secant, the inverse cosecant, and the inverse cotangent. And you can find in our textbook a table which is summarizing all those formulas. Okay, so these are the, so now we are able also to find the derivatives of inverse trigonometric functions. Normally the most important one, okay, are this one and this one. These are the only one which I can tell you immediately. All others I have to derive on my own. So you do not have to, it's not necessary that you memorize all those tables and the derivatives. Memorizing is something you have maybe done in high school, but we do not do this here anymore. Okay, we just remember, okay, how to derive a result. Okay, if we do not really remember it, okay, we can derive it. Okay, so these are the inverse functions of the derivatives of the inverse functions for trigonometric functions. Now we can apply the same for other inverse functions. Another class of inverse functions are logarithmic functions. So the derivatives of logarithms also, this we can now easily handle by the method of implicit differentiation. So we already know that we look at the logarithm to base a of x, okay, and by definition, this means that a to the y is equal to x. Now, we want to apply the method of implicit differentiation to this equation here. Okay, we know that the logarithmic functions are differentiable because of the theorem I told you, namely if you look at the exponential functions, they are differentiable everywhere and do not have horizontal tangents. Okay, so you can apply the method of implicit differentiation here to the right-hand side, and you get the derivative of this function is, as we already know, the derivative of this function here, which is a to the y ln a, times the inner derivative is equal to 1, and we get similar, that's is equal to 1 over a to the y ln a. Okay, so if we plug in the original function, we get 1 over x ln a. Okay, so you see there is only one case where the derivative of the logarithmic functions is in particular simple, namely if a is equal to the natural number. Okay, only in the case where a is equal to e, we get that the derivative of e to the x of ln x is equal to 1 over x. So this is another reason for why we choose, okay, this number e as the basis of our logarithm, okay, because in this case the derivative will get in particular simple. Okay, so we memorized that the derivative of the natural logarithm is 1 over x, and more general, the derivative of the logarithmic function with base a of x is 1 over x ln a. So for instance, if you have the function ln x, and you want to know, okay, what is the derivative, it's now easy to compute. Okay, so we use the chain rule. So we first look at the outer function, okay, and take the derivative. So we have 1 over ln x. Okay, so this was for this function. Now we can forget about this. Now we look at the remaining part. The derivative of the remaining part is 1 over ln of x. Okay, now we forget about the middle function, and we look at the derivative of the inner function, which is 1 over x. Okay, so the derivative of this function is given by this function here. So you see also that the derivative is just defined when x is larger than 1. Because you have to be careful here. This has to be positive. So this has to be larger than 0. So x has to be larger than 1. Okay, and you have similar examples if you have more complicated functions involving logarithms. So next time we will do some more examples, and then we will also look at the derivatives of inverse hyperbolic functions.